We're going to move to the last piece of the chapter, or the book. And in this textbook, it's kind of interesting. They introduce the production of ATP from only the perspective of one energy source, which is glucose, glycolysis, citric acid cycle, and the oxidative phosphorylation. Unfortunately, though, there are three energy sources that we eat: lipids and proteins and sugar. And so we're going to come back and we're going to talk about how we degrade the lipid and the proteins to create molecules that we can create energy from. And so when we do this treatment, we're going to convert the molecules of those entities into energy molecules that we know of. And so we're going to produce things like FAD and NADH. So the FADH2 and NADH, and so we know those go into oxidative phosphorylation, right? Then we're going to break down the molecules into some molecule of a pathway that you already know, okay? And so some of them may get broken down to acetyl-CoA, which is the entrance into the citric acid cycle. And then I assume that you know the citric acid cycle, and then you know how that interfaces to oxidative phosphorylation. For the amino acids, we're going to interact a lot of times into a citric acid cycle intermediate. So once I get to a citric acid cycle intermediate, I'm going to stop because I believe that you know what the citric acid cycle does. But we're going to enter in other pathways too. And so as long as I get it to a pathway that we've covered already, I assume you can take it all the way through to CO2 from that point in time. We're going to do just a little bit of synthesis and some degradation of oddball things. The last chapter is not just amino acids, but anything that has a nitrogen in it. And so there's a little bit of other things in that. And then we're going to look at, and we're going to start with a little bit about lipids themselves and the structure and function. Now, I think the book kind of covers this twice, and it seems like I'm covering this information twice. And I believe some of the things, if you took Biochem 1, you would have seen this. Obviously, you would have seen it also if you're in Cell. But I'm going to go over some of the items that are recovered in this particular chapter. So some of this may be review. All right, lipids. When we think of lipids, the fats, okay, most of the time we think of it as a energy source. Okay, you carry fat because it's a very potent energy source. I'm going to go ahead and turn off the big lights. All right, it's very reduced, and we get our energy from oxidizing. But just like everything else, sugar is not just an energy molecule. It can be structural, it can be informational. Lipids are that way also. Lipids are also structural. Lipids can become cofactors. What's a cofactor? It's what? Something that's inside an enzyme that helps facilitate the reaction. Non-covalently linked, but it's really key for the enzyme to function. A cofactor that we've seen is something like NAD+. It's a reactant that is inside the enzyme that is part of the reaction, and so it's something that binds. It can be electron carriers, and we've seen those. Hormones, intracellular messengers, and emulsifying agents. Ooh, that's a good chemistry word. I just say a word, emulsifying agent. Okay, I say the word. How many people know what emulsifying actually means? I got one. Okay. I have no idea what emulsifying agent is. Oh, I got two. Two people who know. Okay, so why do professors just throw out words out there and just think you know everything? I don't know. Okay, so emulsifying is this. Does hydrophobic things like to be dissolved in water? No, they don't tend to like to be dissolved in water. So an emulsifying agent will have a component within its structure that is very hydrophobic and hydrophilic, so that it can bind to the fatty material and cover it, and then put on the outside a polar region so it makes something fatty more soluble in water. So it emulsifies or is able to dissolve a fat into water. And since we are in an aqueous system within the body, it's important to have emulsifying agents. All right, this slide or something similar you probably have seen before. There are a lot of different types of fats that can be found in the biological systems. And each has a systematic name, each has a common name. Is this list something I want you to memorize? You're praying, oh God, don't let him want me to do this. I don't want you to memorize this, but I do want you to know which one is the most often seen fat within the body. Which one is that one? Number of carbons. The length of a fat that is most common. Ah, I'm going to teach you something today. Number 16. Okay, in that, 16:0 means this. 16 carbons, colon, 0, no unsaturations. Okay. Palmitate or palmatic acid is the name of that. And so it is the most common because that are enzymes that synthesize fats stop at 16. Okay. Now, we have things that are shorter and we have things that are longer. They are synthesized, especially the longer ones, in other places. All right. Well, what about something like this down here? What in the world does that say? It says 20:4 delta 5, 8, 11, 14. What in the world does that mean? Okay, what does the 24, or what does the 20 mean? 20 carbons. What does the 4 mean? 4 unsaturations. Where are the unsaturations? At the 5th carbon, at the 8th carbon, at the 11th carbon, at the 14th carbon. Okay, that particular one is arachidonic acid. We will come back to that particular one and talk about it. It will create intercellular messengers, okay, or hormones. All right, the one thing I do want to direct from this particular slide is something that we can derive from the melting point here. Okay, if you take a look at the melting point, I'm going to make a break line here. What do you see as the pattern in melting points related to a characteristic of the fat you see? Yeah, as soon as you have an unsaturation, the melting points drastically change. What about above the line? What do you see the pattern? The longer they are, the more interactions that they have, or the higher the melting point. What intermolecular force are we talking about that increases van der Waals? That's exactly true. Okay. We've also called it London dispersion. That's also a terminology we've used, but that's in GChem. In biochemistry, we're going to call that the hydrophobic interaction. And so, same concept, different names. But you did see characteristically, as soon as you put in a double bond, if you take a look at 16 with one double bond, its melting point is about 1 degree, whereas 16 fully saturated, it takes 63 degrees to melt that thing and to make it fluid. That unsaturation is huge in disrupting the London dispersion forces. It is because London dispersion forces increase with size, we taught you in GChem, but it also, London dispersion forces also increase when you can pack them very close together. Okay? And if it's a straight chain, they all can pack very, very close together. If there is an unsaturation in a biological system, you get a kink or a bend, and so they cannot pack very well. Now, the unsaturation of a double bond can be in 2 forms, cis or trans. What kind of form do you find the fats in biological system? In the cis or the trans form? It is in the cis form, meaning that on the double bond, both the big things are on the same side. Cis on the same side, right? That's thermodynamically not great, right? Thermodynamically, we don't want steric kindreds, right? We want things in trans, big things away from each other, okay? Biologically, it is very important that the unsaturations are cis because it lowers the interaction between the fats. What kind of fats don't you eat from the commercials that you see? Trans fats are bad. Why are they bad? You're supposed to get a benefit from having trans. You're supposed to have a benefit from having, unsaturations. Naturally, they're cis. That means they will be more fluid at lower temperatures. If you get a trans fat, it will stack just like a fully saturated fat. And so what you're eating are essentially a fat that can compact as much as a fully saturated fat. And saturated fats are very bad news. Why are saturated fats very bad news? They what? They are not fluid. And they are not fluid where in your body? In your arteries and your veins. And that can block up things. All right? Here's the trans, here's the cis. You can see that the trans really kind of binds and looks very similar to the saturated. And the cis is definitely different. Medically, olive oil is a better source of natural fat than beef fat. Why? More unsaturated. If you're going to put a fat on your bread, you can take out the butter stick and slather it on, or you can pour oil, which is fluid and already runny, and put it on your bread. And it feels a little more bougie, okay? But it's better for you, all right? It's European, all right? But it is actually medically better for you. All right. We can have either waxy, that's the terminology about the packing and compacting of the fats, or oily with the unsaturated. All right. Now, quite often, the storage of the energy molecules of fats are done in one molecule called triacylglycerols. Why in the world do we call them triacylglycerols? 3 is tri. What is an acyl? A chain of carbons that has a carbonyl attached to it. And why do we call it glycerol? Because the fats are all connected to one alcohol, which has a trialcohol, and I add 1, 2, 3 fats to it. What is here we go. What is the functional group that I have just circled? I'm sending you back to organic chemistry now. What is that functional group? Is it an amine? Is it an alcohol? Is it an acid? It is an ester. It's an ester. And esters are formed when you react an alcohol with an acid, a fatty acid. Okay? And there is a lot of energy that is contained there. All right. Of all of this energy, a potential energy is a carbon that has hydrogens because I want to oxidize it. All of the fats can be broken down but cannot be converted to sugar. Only the glycerol can be converted to sugar. So of all of those, only 3 could actually feed the brain. The other fats can feed the other organs. Oh, wait. Check this out. What does that say right there? I love it. Okay. Now, why in the world do we store energy as fat? And actually, we store the majority of our energy as fat. Okay? Here is the answer to that question. We store energy in this form so that we can weigh less. Wait a minute. When you add fat, do you weigh less? That's not what we normally think, right? If you add fat, you get fatter, right? Okay, here's where we weigh less if we add fat to ourselves. If you had the same amount of carbons and energy in the form of glucose storage, let's say glycogen, you will weigh more because all of that glycogen has hydroxides, which are surrounded by water, and so you would not only have the carbon weight, but you would actually suck up and hold more water, or retain more water, and you would carry more weight per gram of energy, if it were in sugar form than in fat form. And so fat is a very efficient way to store potential energy in the most compact form that weighs least. Now, for the American diet, here is our problem. We consume a little bit more energy, calories, than we use each and every day. And so we tend to store lots and lots of potential energy. Let's call it that. Okay? And so some of us have a lot of potential energy, and some of us has less potential energy. Okay? Now, one of the other things that fat can work at, and some animals use this, it can be used as insulation. And so some animals tend to use the fat as an insulation source, not just an energy source. That isn't us, though. Yes?
How does it act as insulation?
How does it act as insulation? Like seals, it will create a barrier where heat is not transferred through the body and through the fat stores to get to the internal organs as fast as muscle, and also through the water that's there. You get a layer where there's absence of water, and a lot of the energy is transferred through that water movement, through the water itself. All right. Now, there are some non-metabolic uses for fats. Okay. Anybody been to a Renaissance fair? Yeah, and you can go buy ye old soap, right? Well, what in the world is ye old soap? It's this animal fat put into a big cauldron and lye. Do you know what lye is? It is a form of sodium hydroxide. And what you do is you break the fat down, breaking the ester bond, using the hydroxide, and you get the fatty acid linked to the sodium ion, and you create soap. Okay? Most soap is created in this kind of way. We don't put it in a cauldron and stir it all up anymore. But if you get most soaps and you actually put a piece of litmus paper to it, it will be basic because it has a little bit excess sodium hydroxide on it. Okay? And we create that. Now, when you do it from animal fat, you get all kinds of soaps. We don't do that now in production. What we do is we take a purified fat and then add it to sodium hydroxide until we get a purified, only one single thing. If you actually go back to that list, number 12 carbon fat, if you make it a soap, okay, what you're going to make is the 12 carbon is called dodecadyl, and if you modify it, you get sodium dodecadyl sulfate, or SDS. Have you heard of SDS? Okay, that's just a soap. And if you look on the bottle of your shampoo, what you're going to see, one of the largest ingredients after water is sodium lauryl sulfate. Lauryl is just the common name of dodecadyl sulfate. And so what you use is SDS when you wash your hair. Okay? And what can happen is the SDS, those long chains of fat, okay, can form a micelle. Do you remember what a micelle is? A little ball that has all the hydrophobics on the inside and all the polars on the outside. What it does is it traps all the grease and grime that is in your hair, which if you rinse with water doesn't come out, but if you put it in surrounded by a polar region, then when you rinse out that vesicle, that micelle, it'll rinse out, bringing out the dirt and grime as you wash your hair. All right? And so that's how we can use fats in a non-metabolic use. Okay? Most of us don't eat soap unless your mom gets really mad at what you said. Okay? Now, metabolic use of fats are the kinds of things we think about biochemistry. And so we carry fats around for different types of functions in different ways, because I just can't put the fat in water and it float around. So what I have to do, depending upon where it's coming from, I have to take the fats that I'm ingesting and put it inside a particle, like a chylomicron, or put it inside a particle like a VLDL. What is a VLDL? What is it? What name did you say? Cholesterol? It is not just a cholesterol. Cholesterol is also a lipid that's going to be inside this particle. We've talked about, if you talk about cholesterol in medical terminology, we have LDLs and HDLs, low density lipoproteins, high density lipoproteins. This is very low density lipoproteins. It's a particle that puts the fat inside. If I am actually mobilizing the fat to be broken down, I will actually take it from the adipose tissue, which stores it. I will put it in albumin, which is a protein that floats around in the bloodstream. And the albumin actually has pockets that are very hydrophobic. They are intended to pick up a fat, carry it inside its little cradle, and we carry about 10 per protein, and then deliver it to a cell to have it broken down. That cell, most often, is the muscle cell. Okay? If you have done laboratory experiments, you have to have a reference protein if you're going to calculate protein concentrations. What do you use as your reference protein that you can buy a big bottle of? Has anybody ever made a protein standard? Albumin. What kind of albumin? BSA, bovine serum albumin. It is very easy to isolate because we do slaughter a number of cows, ask McDonald's, and we take the blood, extract that protein out, and it's a standard protein that we use as a reference protein. But we have a albumin in our blood system. What do we call that? It's not BSA, it's HSA. So human, BSA, bovine serum, so human serum albumin. And you can actually buy that to test. Now, they usually don't use human blood. They will genetically make that and then produce it, and we do testing with it. All right, we go to Taco Bell, and you eat meat. All right? Now, that meat will come in, and along with that meat, we'll have some triacylglycerols, okay? And that triacylglycerol will be brought in through the intestine. And the intestine never takes anything in its polymeric form. And this is not really a polymer, but it's a combined form. It actually will break the fats off. It'll break the 3 fats off in the glycerol, and those pieces will come through. In terms of if you eat sugar, it never takes the disaccharides or the polymers of the saccharides. They break them into individual saccharides, and those get absorbed along with proteins. We don't absorb whole proteins. We have to break them down to amino acids before they're absorbed. And we've got all the pieces of the puzzle. We broke them down to bring them in. So what do? Put them back together. And then we compile them into a particle in which the fats are on the inside and the hydrophobic. We have a membrane that's surrounding them. We have proteins that direct where they go. And we send them out into the bloodstream to be extracted or picked up by certain tissue types. Okay. These particular proteins are vesicles. Okay. If you take a look at the and initially it's the chylomicron, which is the least dense material. It has membranes, it has proteins, and it's got stuff all in the middle. That stuff can include the fats. It also can include cholesterol. Okay? These proteins that are on the outside are informational about which tissue type this will bind to and fuse to and deliver the fats to them. And so there are receptors on the outside that will bind these particular proteins and cause a fusion so that things are delivered inside. Okay? And so these particles are important for moving things around. All right. When you get them, it's usually a binding. You break everything down. The lipoproteins are usually repackaged back into a particle and then it's sent back out. It can pick up some proteins and some lipids themselves, but what really happens is it starts with a lot of fat, it delivers to the cell will take what it needs, and then it will repackage what it doesn't, and it will send a particle that has less fat than what it started with. Okay? And you will change the concentrations of these fat particles from very low densities, and as you extract all of the fat out, you get to very high densities particles that have lots of protein with very little fat. And so what we do when we measure cholesterol, we look at two numbers, how much high density, how much low density fat there is, and we add those up. If the concentration is 200 milligrams per deciliter or below, that's considered normal-ish. Okay? There's also a ratio of how much high density to low density. What we really want to do is send out particles that have lots of fats and go to your tissue types and fill all of those fats to replace things that have been used. And so you start off as LDLs and you should end up as HDL as it goes back, and this is repackaged by the liver. Well, you could send out your LDLs, okay, and you go to tissue types and they don't even take up the LDL because I'm full of fat already. And so if you have LDLs floating around for very long periods of time and you never convert them to HDL, then you're also at high risk. So if you have very low HDL and very high LDL ratios, even though you're under 200, you could still be considered high in your what they call cholesterol, but we're really looking at cholesterol and fat together in those tests. Okay? Fats that have been mobilized to be used as an energy source. These are signaled by hormones, like glucagon. You thought you were getting away. You're not. Okay? And the hormone will bind to a receptor. The receptor will upregulate a G protein. The G protein will upregulate another protein to create a secondary signal like cyclic AMP, which upregulates a protein like pKa, which is what happened in the test question. Glucagon upregulates pKa. And that will phosphorylate the enzymes necessary to break down fats, like the hormone-sensitive lipases. Lipase is an enzyme that does what? It aces a lipid. It breaks down a lipid. Okay? And those fats, individual fats, will be mobilized. Even inside the cell, they have to be carried because fats don't like to be in water, so they're carried to the edge, and then they transfer the lipid from one carrier protein that's on the inside to the albumin, which is the carrier lipid in the protein, to take it to the muscle cell. And when we mobilize fat this way, it only occurs when we're in starvation, or we trick our bodies to say we're in starvation by working out. We use the energy molecules to work out, and the concentration of glucose goes lower in our bloodstream because we're working out, and we can mobilize. Now, here's the deal. When doctors are wanting you to lose weight, what do they tell you about working out? You have to do what? Work out 30 minutes a day. Okay, why in the world do they give you a time period? If you work out for very short periods of time, the muscle will use energy sources like the ATP that's there, phosphocreatine that's there, glycogen and sugar that's there. And if you work out for a short period of time, that's all you use. Okay? You tend not to lose weight this way. Now, you tend to not gain weight because you use all of the things that you're eating and you don't convert them into more fat. Have you ever worked out or began to run and you get tired and tired, and then all of a sudden, gets easier. I can go further. What is that called? A runner's high or a second wind? What's really happening in your metabolism is this. You're shifting from your fast energy sources to lipids and proteins. It is taken enough time to get the blood sugar low enough to get glucagon being released. The glucagon goes to the fat storage adipose tissue. It starts mobilizing that fat to be going into the albumin. Then the albumin takes it to the muscle cell, and the muscle cell will then start to break it down. You can only start losing weight if you start breaking down the fat that was stored in the adipose tissue. It takes time for the body's metabolism to shift to using that particular energy source. When you lose weight, where does the mass go? If you're going to lose fat, you're going to work out, where does the mass go? Remember, we have conservation of mass and chemical reactions. It just doesn't evaporate. Where does the mass go? Yes, out. I will accept that answer as a partially right answer. Out how? As what form? CO2. That's where you lose the mass of the carbons. Where do you lose the mass of the hydrogens? Where do you lose the mass of the hydrogens? When you react a hydrocarbon with oxygen, you produce two things, CO2 and H2O. So you get to sweat it out or pee it out. Okay? And so, only if you do what kind of exercise? Aerobic exercise. If by chance you work out really, really, really hard and you feel the burn, are you going to lose weight? You may break down your glucose, get the burn, but it becomes lactate, and that stays in your system and it goes roaming around to be reconverted back into glucose. So you really don't lose a lot of weight doing anaerobic. Now you can build tone, you can build muscle mass, and that muscle mass, even in resting, can use energy, which can eventually cause you to lose weight, but that exercise didn't directly make you lose weight. Only aerobic exercise that allows the carbons to react with oxygen and that can be breathed out and that you can pee out will actually cause you to lose weight. All right. Another place that you can find lipids is structurally. And we find lots and lots of lipids in the membranes themselves. And so for every lipid that is in a membrane, you have two fats. Okay? Two that are directly linked to a linking molecule, or one fat that's linked and one fat that's incorporated into a linking molecule. So we have the glycerol phospholipids and the sphingolipids. Okay. We also then add something that makes it polar, so that it orients in the membrane, so that we have the lipids on the inside and the polars on the outside. And so here's a lot of where your lipids are. And then we have the lipid that is the cholesterol that is also part of this. And so lots of lipids are part of membranes. And the membranes are every cell membrane and every organelle membrane, and there's lots of membranes. And this is not used for energy. It is structural and then can be signaling. We can actually break down a lipid, membrane lipid, and actually use it as signaling. We've seen that process in some signal cell processes or signal transduction pathways. Now, the mix within any individual membrane is quite different depending upon the tissue type. All right, phospholipids are there, sphingolipids are there, cholesterols are there. Okay, proteins are embedded that can do lots of things like transport things through, or metabolic proteins, things that break things down, or signaling proteins or structural proteins. There is a very large diversity of each different membrane type, whether it be different tissue types or whether it be the plasma membrane versus the organelles membrane. All right. The fats that are incorporated into the lipids, so if I look down to the level of this one thing has two lipids attached to it, the kinds of fats that are there, we know that the distribution is different between membranes, but we don't know why or what's important about them. We just know, and we can identify by doing analysis, I have this percentage and that percentage and the other percentage. We just don't know yet why those percentages or differences are important, but they must be because they are different in membranes. It's not just random. Okay, so it's an area that is still being studied. Okay, now the membranes, particularly polar, but in the middle is hydrophobic, they create barriers. That's what a membrane, just with I talk about the lipid and polar regions, are. They are barriers between two pockets, okay? But here's the deal. If you have a membrane that is just a barrier, it's dead. Because what really needs to happen in a biological system is you have to have something going on inside a membrane and something different going on outside a membrane, and you have to be able to bring things in and out selectively and in certain directions for biological function to occur. And so proteins are embedded that actually cause these functions, but when we think about membranes, they are not static. They are dynamic. They free flow. They actually can move around. And so proteins that are embedded in these membranes get the opportunity to float around, and these other lipids float around and they mix up in the membrane itself. It is fluid. So you see things are moving. There's that protein that's in that membrane, and they can be attached either on the surface or all the way through. Okay, the two different proteins are called peripheral on the edges or integral, that's all the way through. Not only the proteins there, sometimes they are just sitting there, and sometimes they are bound by other proteins and fixed. I said that the distribution of the kinds of fats or membrane lipids in there are different. And so if you look at the plasma, the inner mitochondrial, the outer mitochondrial, the lysosomal, the nuclear, you can see different percentages. We just don't know why. We know that they are different. So there is going to be, at some point in time, some reasoning for that. Stay tuned in your career. The fact that membranes are moving is wrapped up in the idea of the fluid mosaic model. And we have membranes that are two-dimensional solutions that have particularly oriented proteins. Okay? That is important because if you have a transporter, like remember we had to transport PI inside the membrane so that we can make ATP, and we had to make ATP fall out and ADP come in. Well, if that protein is oriented in one direction, it'll make ADP come in and ATP go out. But if that protein was put in the membrane the other direction, it would be going in the wrong way. And if you have transporters that are pointed one direction and the other direction, and you open them and activate them, you'll create a circular loop and you would get no movement. You have to control how the not just what protein is in there, but how they're oriented for function to occur. Okay? And we create a barrier for certain proteins and molecules that they'll never pass because there's no protein to move things across. But we will selectively move things that we need into that particular organelle or outside of that organelle in a controlled fashion. Okay? Some of the membrane lipids interact specifically with the proteins to create function. So proteins can typically diffuse laterally. And you can see that big one up there is going, but you see that little tiny one in the background is just zipping along. Okay, it's like over here. It's just moving like nobody's business. Okay? And so, but you see, these proteins never moved. Some of them have underlying structure that link them and place them in one particular place. Some of them are just floating around doing their own thing. Okay? The bigger they are, the slower they move traditionally, because the energy is the same. It's the energy of the 37 degrees Celsius that you are. If you're big, trying to move through that membrane, it's usually slow. If you're tiny, you have a lot of push and can get around. Now, the membranes, if we actually look at the phospholipids themselves, they're wiggling. They're dancing. They're moving around. Okay? If you put in lots of saturated, you don't get a lot of movement. But if you put a lot of saturated, you get a lot of movement. You could also control how much movement it is by heating it up. Check that out. You heat it up, the membrane starts moving. You heat it up enough, you give it enough energy to break the membrane. Okay? Now, we don't necessarily control how fluid our membranes are by heating ourselves up and cooling ourselves down. We do it by adding more unsaturated or less unsaturated. We also modulate fluidity by adding cholesterol. Cholesterol will make it more fluid if you have lots of saturated, because you disrupt that interaction of those very straight chains. But cholesterol makes a membrane more rigid because it has locked ring structures. So cholesterol makes lipids more fluid and makes lipids more rigid. Oh, you're just making stuff up now. Okay? This particular entry of a cholesterol is a modulator. It keeps it closer to the center. It has elements that can disrupt very tight binding and elements of its own structure that doesn't allow it to move a lot and wiggle a lot. And so a combination of the three, how much unsaturated, how much saturated, and how much cholesterol, will make a membrane more or less fluid. Okay? And again, each membrane has their own concentrations, some of which change how fluid the membranes are, which may change how well a protein can move around in that membrane itself.